Okay, so let's move on to the next topic, which is the STT MRAM, where STT stands for spin transfer torque MRAM. Okay, so this is another technique to write information. So unlike the previous case of a magnetic field MRAM, where we send current through two wires to switch one particular MRAM, in the case of spin transfer torque MRAM, we send current directly through the magnetic tunnel junction to write the information. Okay, so the magnetization of this particular free layer will reverse by something called a spin transfer torque mechanism. Okay. So, we will learn what is spin transfer torque, how does it work in the next few minutes. So, before we go on to understand what is STT MRAM and so on, here I want to say why STT MRAM is better than the magnetic field based MRAM. So, first of all, you look at the area occupied by the field based MRAM. So, it is 20 to 30 f square. STT MRAM is only 6 f square. So, as I mentioned, so let us say if f is 7 nanometer, let us make it 100 nanometer. Okay. Easy to calculate. So, if f is 100 nanometer, so 20 f square will be like so 200,000 nanometer square, whereas this will be like only 60,000 nanometer square. Okay, so the area occupied by STT MRAM is smaller. That is one thing that you can see. Secondly, you look at the device, right. This looks quite simple. So, you have a bit line, the current flows through, quite simple lithography. But if you look at this one, it looks very complicated. Okay. So, the number of lithography steps or fabrication steps will be many more in the case of the magnetic field based MRAM, whereas it is quite lower in STT MRAM. Okay, so, these two are some advantages of STT MRAM over the field based MRAM, but the most important advantage is in the scalability. Okay, so, I told you that when we reduce the transistor size or the MTJ size, if current increases, this is a problem we do not want. Okay, so, we want the current to be reduced as we go towards smaller and smaller sizes, which you see here. Okay. So, in the case of STT MRAM, for example, the current that you need to write information goes down as you go towards smaller sizes. Okay. So, this indicates that this STT MRAM technology is scalable. So, when you make the MTJ smaller, the transistors also will be smaller. So, the transistors will be generating lower current. So, all this are possible. Okay. So, these are some of the advantages of STT MRAM. Okay, so, to understand how the STT MRAM functions, so we need to revise some of the concepts that we learnt. Okay, so, in your undergrad or school days, you would have studied angular momentum. So, angular momentum can come from various sources. So, if you take a spinning fidget spinner, for example, here this intrinsic angular momentum, some cases you can have extrinsic angular momentum and so on. Okay. and you can transfer angular momentum from one object to other object. So, last time I asked some of you to rotate the fidget spinner and try to change the direction. So, you will feel some force on you. Okay. So, I will pass around, you can play during my lecture. Okay. So, I just rotate, hold it in your finger, then try to change the angle, you will feel some force on you. Okay. That is because the fidget spinner has some angular momentum, and when you change the direction, you are changing the angular momentum. That means, there is a torque, and that torque will act on your finger. So, you will see that as a kind of force. Okay. So, angular momentum can be transferred. Okay. So, this also something that you need to remember. Okay. So, I will play a video. Okay, watch this video.
Conserved angular momentum. So I'm going to lift my feet off the ground, try not spinning. My assistant's going to come and spin this for me.
Okay, so now the angular momentum is either that direction or this direction.
So I have some angular momentum. Now when I rotate it, start to spin. If I want to stop myself, stop. If I go the other way, I spin back around.
Okay, so he is changing the angular momentum of the wheel, and because of that there is a torque acting on him, which makes him to go around. Okay. So, this is the property that we exploit in the case of spin transfer torque MRAM. Okay. So, to understand the concept of spin transfer torque MRAM, we need to understand two basic terminology. First terminology is spin polarization, then the second terminology is angular momentum transfer. Okay. So, yesterday when we learnt about the giant magnetoresistance concept, I introduced the modes. Modes two current model. So, we learnt that current flows in two different channel, one for upspin, one for downspin. This is something that we learnt, and we learnt that the, let us say if the magnetization is in this direction, the spin up electrons which have magnetic moment in the same direction, they is scattered less. Okay. On the other hand, the spin down electrons which have magnetic moment opposite direction to the direction of magnetization, they get scattered more. Okay, so based on this, we used these terminologies like alpha. I don't know why it's not working. Okay, so if you remember, we used, I don't know why it's not working. Okay. It's not writing.
You can see on some other slides if it's
Mm-hmm. Now it won't work. You have to go to slideshow. Okay, now it's working. Let's go to. Okay. Okay, so we learnt Mott's two current model, and we learnt that the minority electrons whose magnetic moment is anti-parallel to the direction of magnetization, they get scattered. Okay, so the probability of them going through is less, they get scattered. Okay, so this is what we learnt through the alpha. Okay, in ferromagnetic materials, alpha is more than 1, which means the minority electrons get scattered. Okay, so this is something that we learned. Let us say you have a ferromagnetic layer and a non-magnetic layer, and you send electrons from one particular direction. So, this spin up electrons will go through, and the spin down electrons will get scattered. Okay, scattered back. So, they may accumulate here. Okay, so, this probability, I mean this aspect of one type of spin going through a ferromagnetic layer is called spin polarization. Okay. So, it is expressed by this beta. So, basically the difference in the resistivity, or you can express in terms of the density of states. Okay, so, in ferromagnetic materials you have different density of states for spin up and spin down electrons, right. So, the difference in the density of states of spin up electron minus the density of states of spin down electron divided by the sum is called spin polarization. So, what it means is that if you send electrons, majority of the spin up electrons will go through, and a fraction of this spin up also will bounce back. But if out of the several spin down electrons that you send, many of them will return back, only few may go through. Okay. So, the probability of spin up electron going through a ferromagnetic layer with a magnetization like this is higher. The probability of this one going to the other side is lower. Okay. Majority of this will come back. So, that is called spin polarization. The second concept that you need to know is the angular momentum transfer. Okay, so in this case, let us say we send electrons from bottom layer to the top layer. So, this fixed magnetization layer will send this type of spins to the other side. Okay. So, the majority spins will go, and the spins which have magnetic moment in the opposite direction to this, they will come back, okay, or they will accumulate here. Only the spin up electrons will go through. So, I will play the video again. Did you watch the video in the first round? Okay, let me try again. Hmm? Yeah, yeah. Okay, let me split into 2 slides. I think that's better. Okay, so initially the 2 layers are in anti-parallel direction. Initially the 2 layers have anti-parallel magnetization. But when we send electrons through this side, actually we are sending current this way. So, conventionally the current direction is opposite to the flow of electrons. So, if current is, the conventional current is in this direction, electrons are flowing from this direction. So, we are sending spin ups and spin down electrons through this layer. So, when these electrons come to this part, so we know that this will spin polarize. That means, the majority of the spin up will go here. So, a lot of spin up electrons will go, spin down will return back. Okay. So, when these spin up electrons go, they will exert a torque on this layer, okay, just like the rotating wheel passed a torque to the person who was sitting on the stool, right. So, in a similar sense, the angular momentum of the electron spin will exert a torque on the magnetization M. Okay, so that is what you saw in the video. Let us see whether it can play again. Okay, anyway, that is what happened. Because of that, this magnetization changed from this direction to parallel. So, we switched from anti-parallel direction to parallel direction. Okay, so this was possible because of the 2 concepts that we learnt. First concept is polarization, That means, when we send electrons through certain ferromagnetic layer, the electrons with the magnetic moment opposite to the magnetization, they will get scattered back, and the electrons with the magnetic moment parallel to the magnetization will flow across. That is the polarization concept. Secondly, the electrons which go to the other side of the free layer, they will exert a torque. So, there will be angular momentum transfer happening. As a result, the magnetization of the ferromagnetic layer on the other side of the reference layer will switch. Okay. So, this is basically the spin transfer torque switching. Okay. So, here I am explaining the same thing again. Now, no video. So, we have electrons. So, this magnetization is polarizing, which means the electrons with the magnetic moment parallel to this are going to the other side. We are learning about anti-parallel to parallel switching. So, initially these two magnetization are anti-parallel. So, if this is pointing up, the other one is pointing down. Okay. So, when these electrons go to the other side, they will transfer torque to the magnetization here. As a result, finally, this will switch. Okay. So, we will go from anti-parallel state to parallel state. So, the MRAM guys always use the abbreviation. So, they will say AP to P switching. Okay. AP stands for anti-parallel, P is for parallel magnetization. Suppose we want to switch from parallel to anti-parallel, what do we do? What can we do? Yeah, we reverse the direction. Okay. So, instead of sending electrons from this side, we send electrons from the other side. Okay. Now, the initial configuration is both the magnetization are parallel. Okay. So, now we send electron from this side. So, we have spin up electrons, spin down electrons. So, this layer has magnetization pointing in this direction, and this layer also has magnetization pointing in this direction. So, when you send these two, the spin up electron will go through, it will do nothing, but the spin down electrons cannot go through this layer. Okay. You know that it will be scattered, right. So, these scattered electrons will accumulate here. So, you will have an accumulation of spin down electrons, and they will switch the magnetization. So, when you have a lot of spin down electrons, they will exert a torque on the magnetization of this layer and switch it to be anti-parallel. So, this is how we achieve parallel to anti-parallel configuration.
In the first kind of switching, switching is because of electrons which get passed through. In this kind, it is because of electrons which get accumulated.
Yeah, accumulated. Yes. Yeah.
And but they are minority, right? Lot of current may need for this.
Yeah. So usually AP to P needs less current compared to parallel to anti-parallel, slightly more current. Yes. Initially, free layer will be anti-parallel. I mean, we do not know whether free layer is anti-parallel or parallel. So, it is just that if you want to write 0, you send current in one direction. If you want to write 1, you send current in the opposite direction. Okay. So, in a memory you do not know whether the memory is in 0 or 1, you do not know whether it is parallel or anti-parallel. So, just depending on whether you want to write 1 or 0, you send the current in one direction or the other direction, that is all. Okay. So, this spin transfer torque concept is again coming from magnetic recording. Okay. So, I told you magnetic recording is the father of all MRAM related technology, okay, except SOT that we will learn later. So, when people studied the read sensors, right. So, in read sensor, for example, GMR or TMR sensors, we have one reference layer and one free layer. We send current through the layers to read the resistance state, right. So, if the recording media is making them parallel, we will have low resistance. If the recording media magnetic field is making them anti-parallel, we will have high resistance. Okay. So, we are sending a current which is called sensing current to read the bits in hard disk technology. Okay. So, when people were studying this one, they realized that the current you send through the sensors is affecting the magnetization. Okay. So, they noticed that the current you send through the sensors for reading information is affecting the magnetization state. Okay. So, at that time two scientists, one is called Slonzewski, I may be wrong in spelling, and another scientist called Berger. So, these two predicted that, I mean theoretically they predicted that if you send current through something like this MTJ or something like that, the current you send is causing spin transfer torque. Okay. So, this was a theoretical prediction in 1996 based on magnetic recording principles. Okay. So, when you are talking about magnetic recording principle, you do not want the magnetization of the sensor layers to be affected by the current that you flow. Okay. So, this magnetization should be parallel or anti-parallel only because of the magnetic field that comes from the recording medium. It should be independent of the sensing current. Okay. So, this was considered like a negative effect, unwanted effect. So, in the case of read sensors of hard disk drive, this current affecting the magnetization states is the unwanted effect. Okay. So, it was proposed in 1996. Then somewhere a few years later, people realized that we can use this to write information. Okay. So, people thought that okay, we have this spin transfer torque effect, why do not we use this to switch MRAM. Okay. So, with that objective, people have started studying whether we can switch the magnetization of MRAM by sending current through the device. Okay. So, this is one of the earliest studies of spin transfer torque switching. So, around 5 years after the theoretical prediction, people showed that you can switch magnetization of MRAM layers by sending current through them. Okay. So, in this case, this is a GMR. So, you have a copper spacer CPP GMR. Okay. So, you are sending current perpendicular to the plane. This is a CPP GMR device. So, you have two ferromagnetic layers cobalt separated by a copper spacer. So, this is a CPP GMR, you are sending current through this way. Okay. So, if you look at this graph, it does not have any magnetic field. Okay. there is no magnetic field, sorry, this is the there is no magnetic field, and you only see the current in the x axis and resistance here. Okay, let us say we start from here. We have certain current and we go towards the other direction. Then suddenly you see a change in the resistance. Okay, that is because the current in this particular direction has changed them from parallel state to anti-parallel state. So, you have low resistance when the magnetization are parallel, right. You have high resistance when the magnetization are anti-parallel. Okay, so, they notice that at certain value of current, this device switches from parallel to anti-parallel. So, now you have high resistance, because now they are in the anti-parallel state. Now, you go along this line, change increase change the current direction. So, now negative to positive, at certain value you see that it has switched from anti-parallel to parallel configuration. Okay. So, here they did not apply any magnetic field, only by changing the current amplitude and the current direction they can go from parallel state to anti-parallel state. So, this experiment proved that we can switch the magnetization states by sending current through the device and by using spin transfer torque mechanism. So, this graph also answers your question, right. So, when you go from parallel to anti-parallel, we need more current. Okay. When you go from anti-parallel to parallel, you have less current. Okay. So, this video summarizes everything that we discussed. So, initially we have anti-parallel state, we are sending electrons from this side. So, the majority electrons go to the other side and switch the magnetization from anti-parallel to parallel. Now, we are switching from parallel to anti-parallel by the spin accumulation here. Okay, so, this is basically the spin transfer torque switching mechanism.
So, that accumulated electrons, then where it goes in last, like when the switching is done?
Yeah, I mean, I haven't thought about this one, but this is a metal. I am not sure, maybe another time I will tell you. Okay, so, now the theory part, you do not need to worry too much if you do not understand. Let us say you have a magnetization, okay, shown by this red color arrow, and you apply some magnetic field. Okay, so, this is what we normally do, right. We take magnetic material with certain magnetization. When we do hysteresis loop, this is what we do. We have magnetization in one particular direction, we apply certain magnetic field, and what this magnetic field does to the magnetization at smaller time scales. Okay, we are now talking about time scales in the order of picoseconds, what happens. Okay, so, if magnetization is pointing in this direction and you apply magnetic field along this direction and there is some angle. Okay. So, this magnetic field will cause a field like torque. So, what happens, this magnetization will precess around this magnetic field. Okay. So, the magnetization will go around like this. So, if magnetic field is like this, magnetization is like this, it will go around like this, precess like this. Okay, so, the precession path is shown here. So, that term is called field like torque, it is given by this formula. So, it is in the direction perpendicular to both the magnetic field as well as the magnetization. That is one thing. Secondly, this precession cannot happen forever. Okay. So, in systems when this kind of precession happens, some energy transfer happens. So, finally, the magnetization precession will be damped, okay, which means the precession will slowly die down, and finally, this magnetization will point along the direction of this magnetic field. Okay, so, this damping is given by this formula. So, is a cross product of m and dm over dt. So, m is along this direction and dm dt is along this direction. So, basically this damping what it does is it brings the magnetization parallel to H. Okay. So, the damping torque moves the magnetization parallel to H. How many of you here do LRG simulation? 1, 2. Okay. So, if you are doing mu max simulation, mu max 3 or WUMF, so basically you are using LRG equation. So, in LRG equation, the Landau-Lifshitz part LL is by two scientists, Landau and Lifshitz. They came up with this term that if you have a magnetic field at certain angle with respect to magnetization, magnetization will precess. That is the term introduced by Landau and Lifshitz, and Gilbert is the one who introduced this damping part. Okay. So, after Gilbert's introduced the damping part, so we know that this magnetization will finally settle along the direction of magnetic field. So, these things happen, and you should know that torque is the equivalent version of force in rotational motion.
So, why you were writing for that H effective?
Pardon?
H effective.
H effective is some magnetic field. Okay. For example, let us say you have only one particle, okay, only one particle with the magnetization like this, and you apply a magnetic field. Okay. So, this is applied field. You can say that this applied field will do the same thing as what is shown here, but in a system there may be many other sources of a magnetic field. Okay. So, it need not come only from the magnetic field that you apply. So, there can be say magnetic field from the neighboring atomic moments and so on. So, this effective field is the field seen by this particular magnetization. So, it can be coming from any other source. So, when we do LLG equation based simulation, so this H effective can be coming from the external field we apply. So, we usually call this at H Zeeman. Okay, then this H can come from the anisotropy. There are so many sources of this H effective. So, this H effective will include all the terms, different terms that a particular magnetization sees inside the system. Okay, so now we go on to the STT. So, we are sending electrons from left to right. Okay, so, this is the free layer that we want to switch. Okay, so, this is the reference layer or polarizing layer. Okay, so when you send electrons through this layer, so we have learnt about polarization. So the electrons which are in the same direction as the magnetization go through to the other side. Okay, so when these electrons go to the other side, this free layer magnetization will experience one effective field given by this term, and it will also experience a torque given by this formula. Okay, so normally what you do when you do the simulation of hysteresis loop or something, we normally only do two terms. Okay. So, if you are simulating a hysteresis loop M versus H, then these two terms are enough. Okay. But when you are simulating spin transfer torque, for example, so in that case you have to include these few terms, okay, coming from the transfer of these electrons to the other side and the torque these spins exert on the free layer and so on. Okay, so these are the terms that people use in the energy equation to study the spin transfer torque. Okay. The most important concept that you should remember here is that the projection of this particular M perpendicular to the free layer is the one that gives rise to the torque. Okay. Let us say this is your M pin. Okay. So, it can be resolved into two components, right? One is the blue and another one is along this one. Okay. So, only this component which is perpendicular to the magnetization will cause torque. Okay. So, when many electrons go to the other side, this component keeps changing, I mean this component keeps exerting a torque on the magnetization. So, these two should be perpendicular. Okay. Only the perpendicular component causes the torque. Okay. So, in a toy quantum mechanical model, what happens is that when a spin of this type goes to the other side, it will make the magnetization tilted by a certain angle and it will bounce back like this. So, angular momentum transfer is shown in this picture. Okay, so, we call the reference layer with many names, right. I told you we can use the word fixed layer, hard layer, reference layer and so on. We can, some people also use the word polarization layer for the same reference layer. Okay. So, what we expect from the reference layer of a STT MRAM is that the reference layer should have as high polarization as much possible. Okay. So, if the polarization of that material is high, then we can achieve switching better. So, that is one criteria. The second criteria is that this reference layer should be extremely stable. That means, the current you send through the STT MRAM should switch only the free layer. Okay. So, that current should not switch the magnetization of this layer. So, the reference layer should be always pointing in one direction. So, that is second criteria. Either we can choose a material with a large coercivity or we can pin the reference layer using exchange bias. So, that is second point. And when it comes to the reading part, the TMR depends on the crystallographic texture of the magnesium oxide. So, this one we will do day after tomorrow. So, day after tomorrow you will learn that this magnesium oxide has to be in 001 texture. So, that will give rise to high TMR. So, when we design reference layer, we should design in such a way that the reference layer does not affect this 001 texture of magnesium oxide. Okay. So, that is the third condition. So, it should not deteriorate the 001 texture of magnesium oxide. Okay. So, when you write I mean when you switch magnetization from one direction to the other direction, it does not flip like this. Okay. It goes through a precision mechanism. So, we learned that the different torques will make the magnetization to switch in certain path. Okay. So, if you apply current for a short time, let us say you apply certain pulse width. Okay. So, you apply certain current pulse with a certain pulse width. So, if this current amplitude is lower than what is required, what happens is that maybe your spin will persist for some time, then finally settle in the same direction. So, switching will not happen. Only when this amplitude meets the critical current, we can achieve reversal. Okay, so, I will show a few animation. So, here the pulse you apply, the current is not below the critical current. So, you see that the magnetization just oscillated, then it did not switch. So, if the current is too high, if it is more than the critical current, then it can switch faster. Okay. So, even though your pulse width is so large, you can switch much before your pulse ends. Okay. So, what it means is that during all this time you are wasting energy. Okay. So, people normally choose the right, I mean the critical current for that pulse width. Okay. So, if you choose the right current for the right pulse width, then you can achieve effective switching. Okay, let us do some questions. You need to log in again. So, let us go to the questions. Okay, regarding your question, what will the accumulated spins do, right? So, we are talking about metallic layers. So, in metallic layers the electric field cannot exist, right. So, the accumulated spins should go back. I mean spins cannot accumulate and they will go back, right.
So the same wire from the
They will go back to the other side. Yes. Accumulation of electron will give rise to electric field, so it cannot happen. But in semiconductor, I don't know. Your case, I don't know. Okay, so let's look at the result. Okay, many of you are wrong. The reference layer is doing two things, right? So, let us say you go from parallel to anti-parallel. So, you are sending electrons this way. Okay, so, the spin up electrons go out this way, but the spin down electrons get reflected back, right. Spin down electrons accumulate here and they are the one causing the reversal of this magnetization from parallel to anti-parallel. Okay, so, in this geometry the reference layer reflect electrons into the free layer. On the other hand, if you go from anti-parallel to parallel, you are sending electrons this way. So, spin polarized electrons go to the other side and reverse this from anti-parallel to parallel. Okay. So, in that case you are sending spin polarized electrons into the free layer. So, in one case you are sending spin polarized electrons into the free layer, in the other case you are reflecting spin polarized electrons into the free layer. So, C is the correct answer. So, all of the above is the correct answer. It is doing both. Next one. Parallel to anti-parallel, we send do you know why many of you are wrong? Yeah, so I'm just saying current. Okay, so conventionally current and the electron flow are in opposite direction. Okay, next one. Oh, here again. Here I am talking about electrons, right? So, to switch from anti-parallel to parallel, okay, let us go back. To switch from anti-parallel to parallel, we are sending electrons this way. Okay. So, they get spin polarized. So, the spin up electrons come to the other side and switch the magnetization. Okay. So, the electrons are sent from reference layer to the free layer. So, this is the correct answer. Okay, so, now we move on to the next topic. So, currently the STT MRAM is already a product, as I told you. People are using STT MRAM as a e-flash memory. So, STT MRAM can be operated at around 10 power minus 12 ampere per square. So, the current density that you require to operate STT MRAM is typically around 10 power 12 ampere per square meter. Okay. So, people are looking at, okay, this is one thing. Secondly, STT MRAM can operate at speeds of in a time scale of 10 nanoseconds. So, typically like say 100 megahertz kind of thing. Okay, so, that is the speed in which STT MRAMs can operate. So, people are thinking of how can you increase the speed, whether you can go from 10 nanoseconds to 1 nanosecond kind of time scale, and whether you can reduce this current density from 10 power 12 to say 10 power 11 or 10 power 10 ampere per square meter. So, these are the questions the researchers have. So, we want to make faster devices, we want to make devices that consume less power. Okay. So, in that aspect people are working on another type of MRAM called spin orbit torque MRAM, SOT MRAM, which stands for spin orbit torque. Okay. So, this spin orbit torque MRAM operates on this physics called spin orbit coupling. Okay. So, spin orbit coupling is the interaction between the spin angular momentum of an electron and the magnetic field generated by its motion around the nucleus. Okay. So, that is too wordy. So, let us look at what happens. So, you have certain nucleus. So, nucleus has protons. So, it has a positive charge and the electrons are orbiting around. Okay. So, this is from proton's point of view. So, proton is looking at electron going around. Okay. But if you look from the electron's perspective, it is like the proton is going around. Okay. So, if you look from the electron's perspective, a charge is going round. Okay. So, we learnt that in solenoid, right, in solenoid you are sending current through a loop. Okay. So, current through a loop produces magnetic field, right. So, we learnt before. So, in this case this is a charge going around. So, that is like a current flowing around. So, this electron will see a magnetic field. Okay. So, when electron goes around a nucleus, basically the electron will see a magnetic field, and that magnetic field is given by this formula. Okay. So, it depends on the charge of proton and the number of protons inside the nucleus. Okay. So, this is the magnetic field. So, the magnetic field and the spin will interact. So, there will be a shift in the energy of electron. Okay. So, spin up electrons will have, so spin up and spin down electron will have different kind of energies. Okay. So, this is basically the spin orbit interaction, and we can observe the spin orbit interaction by observing the torque exhibited by the spin orbit coupling effects. Okay. So, when people talk about spin orbit torque, we are talking about some heavy metals. Okay. So, if you remember the formula I showed you, there was a G, right. So, if the G is large, then the magnetic field is supposed to be large. Okay. So, in heavy metals have a large number of protons, right. So, in heavy metals G is large. So, this B is going to be large, then the spin orbit coupling is going to be large. So, when we talk about spin orbit torque MRAM, we always deal with heavy metals like tungsten, platinum, tantalum, all these are some examples of heavy metal layers in which we have observed spin orbit torque. Okay. So, because of the spin orbit interaction, so I told you that it is spin dot B, right. So, one type of spin will have one energy, another type of spin will have another energy. Okay. So, because of that, when you send a current through a heavy metal layer, one type of electron will go to one side, another type of electron will go to the other side. Okay. So, this is called spin Hall effect. Okay. So, normally what do you say when you say Hall effect? So, what we do, we take a semiconductor, for example, we apply a magnetic field. So, because of this magnetic field, electrons go to one side, holes go to other side. So, if you measure the voltage, you will see some voltage, right. So, in the case of normal Hall effect, you will see a voltage because electrons go to one side, holes go to another side because of the magnetic field that you apply. Okay. So, when we talk about spin Hall effect, we do not need to apply any magnetic field, but because of the spin orbit coupling, there is already the S dot B interaction. Because of that, one type of electron, say for example, spin down electron goes to this side, spin up electron goes to the other side. Okay. So, this is called spin Hall effect, and you can use this effect to switch the magnetization and make MRAM devices. Okay. So, this spin Hall effect was proven experimentally somewhere in 2012. Okay. So, in this case they deposit tantalum. Do they show the detail here? Okay, I think this is tantalum, even though the slide does not show. So, they have a heavy metal layer like tantalum on at the bottom, then they have a ferromagnetic layer on top. Okay. So, at first they measure the anomalous Hall effect. So, anomalous Hall effect is another form of Hall effect, which is which can give rise to the information about magnetization. Okay. So, if the resistivity shows you this kind of hysteresis loop, so it is like measuring magnetization as a function of external magnetic field. Okay. So, anomalous Hall effect is quite often used to measure hysteresis loops electrically. Okay. So, electrically anomalous Hall effect can give rise to loops like this. So, in this study they are measuring the magnetic properties of this ferromagnetic layer using anomalous Hall effect. So, at first they demonstrate that this magnetic material shows hysteresis loop like this. Okay. So, in the next slide what they do is they send a current through the tantalum layer. Okay. So, here the external, there is a little bit of external magnetic field, okay, but this is fixed, this one is constant. Okay. It is not changing when they do the experiment. Okay. So, what they change is the current they send through the tantalum layer. Okay. So, they send current through the tantalum layer, and because of this current they see switching. Okay. So, magnetization is initially in this direction. So, at some current it switches to another, say let us say magnetization is like this or like this. Okay. Then again when they sweep the current, they see the magnetization going from that direction to this direction. Okay. So, they can see the magnetization switching just by sending current through the tantalum layer. Okay. So, what happens is when they send current, let us say now this is a cross sectional view. So, this is a tantalum for example. When you send the current through the tantalum layer, so one type of spin accumulates here, another type of spin goes into the opposite direction, then you can see down spin is here, up spin is here. Okay. So, they typically follow this circular relation. So, spins go all over to the different edges of the heavy metal layer. So, when this type of spin goes up, it can switch the magnetization from pointing left to right. Okay. So, here you notice that there is no special polarizing layer. Okay. in the case of STT MRAM, you had a ferromagnetic layer, that ferromagnetic layer polarized your spins, and because of that polarized electrons you were switching. But in the case of spin Hall effect, you are just using a heavy metal layer like tantalum or tungsten, and using the spin Hall effect you accumulate certain type of spin which helps to switch the magnetization. Okay. So, this is called spin Hall effect. Yeah.
In the previous slide,
Mm-hmm.
is that negative resistance? So it is
Negative resistance. So, what it means is they apply some current, they measure the voltage, and for calculating the resistance they will just divide this voltage by so okay, let me tell you what they do exactly. So, a Hall bar looks like this. Okay. So, when we do anomalous Hall effect, so the anomalous Hall effect, the anomalous Hall bar will look like this. So, we send the current through this side. Okay. So, we have current going through this one, and we measure the voltage across this. Okay. Across these two sides we are measuring the voltage. So, this voltage depends on the spin accumulation, say let us say one type of spin is here, another type of spin is here. So, because of this difference in the number you will have some voltage. Okay. So, when they plot resistance, they are dividing this voltage by this current. Okay. So, it is not like so when you measure the resistance of this wire, for example, let us say you have a wire, you want to measure the resistance of this wire, we use the term RXX. So, we have two current leads, then two voltage leads, then you divide this voltage by current to get RXX, right. But in this case we are measuring RXY. That means current is flowing in the x direction, you are measuring the voltage in the y direction. So, you are dividing this voltage by current. Okay. So, this voltage will depend on whether the magnetization is pointing into the board or pointing towards you. Okay. So, this voltage will be like positive or negative irrespective of this current direction. Okay. So, because of that you will see sometimes positive, another case negative. Okay, so people use some terms like spin Hall angle or spin, torque, efficiency to determine how efficiently we can switch information, switch the magnetization using the spin Hall effect. So, spin Hall angle is basically defined as the ratio of the spin current by charge current. Let us say you send certain charges here and how much of that results into spin current, and this ratio is called spin Hall angle. So, sometimes people also use the word spin torque efficiency. Okay. So, if you want to make spin orbit torque MRAM, okay, now let us see how we can use the spin orbit torque to switch and make MRAM devices. Okay. So, a spin orbit torque MRAM may look like this. So, you have two transistors, they provide current. So, this current flows through the heavy metal layer, and because of the spin orbit torque, certain type of spin goes into this free layer. Okay, so, this is an MTJ. You have free layer magnesium oxide reference layer, and you are switching this free layer magnetization by sending current through the heavy metal layer. Okay. So, this heavy metal layer sends certain spin to this layer, and because of that you can switch the magnetization. Okay. So, this is the design of SOT MRAM. So, there are some benefits and problems of this particular design. Okay. First, let us look at the benefit. For that, let me go back to the empty screen. So, in the case of STT MRAM, right, STT MRAM, you have a magnesium oxide layer, then you have a reference layer, and you have a free layer. Then you are sending current either this way or in the opposite direction to switch parallel or anti-parallel. Okay. So, here the read and write path are the same. So, if you want to write information, you send current through this path. If you want to read, whether it is 0 or 1, again you are sending current through the same path. Okay. So, the read and the write lines are the same.
Don't there is the risk of flipping the bit while reading?
Okay. So, what we do when we read, we send a smaller current. Okay. So, we do not want to switch the bit when we read information. So, for this reason the write current is more than the read current. Okay. So, the advantage of the STT MRAM is you just need one transistor. Okay. One transistor is enough. So, it can supply current to write information, and it can supply current to read the information. So, basically you need only two terminals. Okay. So, let us use this word, only you need two terminals, okay, terminal 1, terminal 2. With just two terminals you can read and write information. Okay. So, it is less complex. But the problem with this design is, I told you that the writing current is larger than the read current. So, the writing current goes through this device. So, let us say we write billions of bits. So, every time you write information, so the device will get heated a bit, right. So, there is a Joule heating. So, if the device has a resistance R and this is your write current. So, there is some Joule heating produced. So, when there is some heating, there will be some diffusion of atoms. Okay. So, maybe some atoms of magnesium will go, or sometimes the oxygen atoms may go somewhere. Okay. So, when you do repeated writing operations, this tunnel barrier, the magnesium oxide may break down. Okay. So, in the MRAM industry, they use this terminology TBBD, which means tunnel barrier breakdown. So, after many operations of writing, because the write current is quite large, it can damage the magnesium oxide layer. Okay. The tunnel barrier may break down. So, this is the problem of STT MRAM technology. But when you go to the SOT MRAM technology, your MRAM look like this. So, we have free layer at the bottom, reference layer at the top, magnesium oxide is here, this is your heavy metal. So, when you are writing, you are sending the current through the heavy metal. Okay. So, this is the writing path. When you are reading, you are sending. Let me use another color. Okay. So, for reading you are using another path, for writing you are using different path. So, the writing current is larger than read current, right. But the larger current is now not going through this device. Okay. So, it is going through the heavy metal. So, heavy metals are usually reasonably good conductors. So, they pass the current relatively without much problem, and this tunnel barrier does not break. Okay. So, this is the advantage side of SOT MRAM. So, you do not have the tunnel barrier breakdown. So, you do not have this problem in SOT MRAM. Secondly, SOT MRAMs can be operated at 10 power 11 ampere per square meter. So, the current density is typically 10 times lower. So, if current can be 10 times lower, power can be like 100 times lower. Okay, so, these are some of the advantages of spin orbit torque MRAM. Okay, so, current passes through the barrier only during the reading. So, tunnel barrier does not break down. So, these devices have a longer lifetime. Okay, but the disadvantage is now you need 3 terminals. Okay, so, you need 2 terminals for writing operation, another 2 terminal for reading operation. Okay, so, 3 terminals occupy more space and the device is a bit more complex. Okay, so, there are disadvantages and advantages of SOT MRAM, and I will show some more slides to show some other advantages. Okay, so this slide summarizes everything about STT MRAM and SOT MRAM. So, in the case of STT MRAM, usually see the switching speed is around 10 nanosecond. If you go lower than 10 nanosecond, you need more and more current. Okay. So, this is like energy, you need more energy to switch, but if you operate around 10 nanoseconds, you do not need to spend much energy. So, this is the feature of STT MRAM. On the other hand, SOT MRAM, you can operate at 1 nanosecond, okay, without much additional energy. So, SOT MRAM help to achieve high speed. So, because of this reason, people are thinking of using SOT MRAM as a replacement for SRAM. SRAMs also operate at high speed around 1 nanosecond. So, people are thinking of replacing SRAM with SOT MRAM. So, if you are not worried about the speed, you can use STT, but applications like SRAM where your speed is very important, you can use SOT. Okay, so people have, I mean, this one result I wanted to show. People have studied SOT MRAM in different configuration. So, these two are like in plane MRAM, right, where magnetization is parallel to the disk surface. Then this one is a perpendicular. So, here again we have two different type in plane. One is called type X, where the magnetization is in the same direction as current. Type Y means magnetization is perpendicular to the direction of current. Okay. So, let us say this is a heavy metal layer. When you send the current in this direction, let us say x direction, you are sending current. So, that will produce spin polarization along the y direction. Okay. So, the spins pointing along the y. Okay. So, let me zoom this one. So, this is x, this is y, z means perpendicular. So, when you send current in the x direction, the spins will be pointing in the plus y or minus y direction depending on your current direction and the material property. Okay, the spin that goes up towards the ferromagnetic layer is pointing in that direction. Okay. So, if magnetization is pointing anti-parallel to this spin, so this spin will exert torque on this one, then switch. Okay, that is quite normal, we learned that before. But if you want to make these spins to switch either perpendicular magnetization or magnetization at an angle of 90 degree with respect to this spin, usually we need to apply certain magnetic field. Okay. So, we call that symmetry breaking field. Okay, so, you do not need to worry too much about all these things. basically you can make MRAM in 3 geometries, but I mean this is only physics study. We are not going to use these 2 in products, because we are going to use perpendicular MRAM. So, basically you need to apply certain field Hx. So, you need to apply a magnetic field along the direction of your current to break certain symmetry. Okay. So, when we talk about breaking symmetry, what it means is when you send this spins in the y direction, we usually use the symbol sigma y. So, this sigma y spins are going to the ferromagnetic layer. So, this sigma y spins can switch the magnetization from perpendicular, I mean pointing up to pointing down, but this is not stable. So, again these spins can act on this magnetization and they can make it perpendicular. So, these two are equally almost same energy. So, they will just go up and down. You cannot keep the spin in one particular direction. So, to break the symmetry, we usually use a magnetic field in the x direction. Okay. So, out of so many things as I show in this picture, only this is relevant for application. We will be using perpendicular MRAM. So, in perpendicular MRAM, we send a current in one particular direction, and we need a magnetic field along the current direction. But people are trying to overcome that problem. So, when you make MRAM and sell it to people, you want to operate without that Hx field. Okay. So, you just only want to send current through the device to switch. Okay. You do not want this one. So, there is lot of research going on how to achieve field free switching. Okay. That means, without this Hx can you switch the magnetization. So, for that people are trying to use some antiferromagnetic layer below the perpendicular magnetic layer, or I mean there are many other topics. Even in my group we are doing a lot of research on how to achieve field free switching, and you do not need to worry about all these things. Okay. As a summary, we can switch the magnetization of the free layer of MRAM. So, switching free layer magnetization of MRAM is called writing. Okay. So, this writing can be achieved using magnetic field. So, you can send current through 2 orthogonal wires and achieve switching. That is what we learned first, and this technique is extinct. Nobody uses this one. The second candidate is using the spin transfer torque principle. So, you can send current through the device, you will generate some spin torque, and you can use this to switch magnetization. We did not discuss this today, and we can also use spin orbit coupling. So, use spin orbit torque to generate spins. So, these spins are purely coming from non-magnetic materials, okay, like heavy metals, iron, platinum, sorry, not iron, platinum, tungsten, tantalum. These kind of materials are used for generating spins into the ferromagnetic layer, and we can switch magnetization. So, we learned these 3 topics today. Okay. Any questions? Yeah.
What is the principle behind removing this HX?
Using the Hx, is it?
No, like
Hmm?
in this slide we are using antiferromagnetism. So
Hmm. Okay. So, how the antiferromagnetic material will overcome, I mean help in the Hx? Okay. let us say this is a magnetic material with a perpendicular magnetization. So, in the absence, let us say you only have heavy metal layer, the magnetization will be like this. Okay. Now, let us say you deposit this ferromagnetic layer on top of antiferromagnetic layer. So, this antiferromagnetic material has spins like this. So, there is a horizontal component of magnetization at this edge compared to the other edge. Okay. So, the magnetization, if you go from top to bottom, maybe they are something like this. So, you have some canting of spins in this region because of the interaction of antiferromagnetic material with this part of the ferromagnetic layer. So, you have some canted spin. Okay, so, you can imagine that this is like having two components. Okay. So, this component helps in getting rid of the HX.
And this spin polarization will be possible in AFM.
Yeah, spin polarization is possible. I mean, yeah, in this case they have shown iridium manganese as the heavy metal layer. Yeah, I mean they have demonstrated this, so it works.
Like, one question. Can you replace this heavy metal with some composition which have high spin Hall effect coefficient?
So, you are saying whether we can, so you are talking about doping or?
No, like the people who are trying to, like working on layered materials
Mhm.
such as high spin Hall effect signals. So that can replace the heavy metal in this architecture or not?
Okay, there are a lot of research on which is the best material to have spin Hall effect. So, so people normally use like platinum, tungsten or tantalum. These are standard materials when you just want to focus on other aspects, okay, where spin Hall effect is one mechanism that you use. Okay. Then if you want to enhance the spin Hall effect, there are lot of research directions. So, some people use I mean study doping, say platinum with tantalum or tantalum with copper. So, people try doping, that is another way. Then people are also looking at what do you call the while semi metals, topological insulators. So, a lot of materials are being studied to see whether we can achieve high spin torque efficiency. So, while semi metal, topological insulators all are being studied. Yeah. So, that is one aspect. So, in my group we are also looking at another phenomenon called the orbital Hall effect. Okay, so let us say you have some material. So, in this case we are looking at light metals like chromium, those kind of light metals. So, we send current. So, here one type of one type of orbital electrons go one side, another type of orbital electrons go to another side. So, we have orbital Hall effect, but orbital Hall effect cannot be coupled to magnetization. Okay. So, orbital Hall and orbital part of electron and magnetization cannot be coupled. So, what we do, we exploit the LS coupling. So, we convert orbital torque into spin torque through some mechanism. For example, let us say you have chromium is the orbital Hall layer. So, there is a orbital Hall effect. We convert that into spin Hall effect by having let us say thin layer of platinum. So, we have Ls, then we generate spins that go up to the ferromagnetic layer. So, S can be coupled to M. Yes. Then with this Ls conversion we can switch the magnetization. So, there are a lot of research going on. So, whether you can investigate on doping materials or you can investigate exotic materials like topological insulator, wild semimetals, or in another direction you can look for new effects like orbital Hall effect to switch. So, lots of research is going on. Slide 36 elaborate again about resistance of parallel and okay, slide 36 is one of the earliest demonstration of spin transfer torque switching. So, in this case they are trying to switch the magnetization of the ferromagnetic layers with no magnetic field. Okay. So, normally when we do hysteresis loop we switch magnetization with a magnetic field. So, in this case there is no magnetic field at all. Okay. So, they send the current through this device. Okay. So, either they send current downwards or they say they can send current upwards. Okay. So, we can call one of them positive, another as negative. So, if we start from this point, so you can see that there are two states, one is this state, another is this state. Your y axis is the resistance. Okay. This is resistance. So, this is basically high resistance, this is low resistance. Let me use a different color. Okay, the green line is low resistance state, red line is high resistance state. So, we know that the resistance will be low when the two layers are parallel to each other. And we also know that the resistance is high when the two layers are anti-parallel to each other. So, this is a GMR device. So, this is a ferromagnetic layer, copper spacer, ferromagnetic layer. So, this is a GMR device. Okay, so, let us say we start from point A in this picture and go towards negative current. So, we follow the green line path. Okay. So, starting point we are in the parallel state. So, when we go towards certain current say minus somewhere here, we can see that the resistance has changed. It has gone to a high value, which means at this particular current we have achieved anti-parallel configuration, which means the magnetization of the one of the layer has switched from being parallel to anti-parallel state. Okay, so, we come to the point B, we achieve switching. Then again when you go from point C towards let us say point D. Okay, when you go through C, B, D, you are in the state of high resistance, then at some point D you are switching to a low resistance state. Okay, so this is what I demonstrated. Okay, got it. Thank you. Any other question?
Yes, sir.
Yeah.
So in SOT, different types of geometry. Type Y and type X are in-plane geometry.
Yeah, yeah.
Why they are not considered? Because type Y already has a possibility of field-free switching.
Yeah. Type Y is considered for some specific applications, like that particular group in Tohoku University. They are using type Y for some form of computing. Okay. So, for that particular application type Y is useful, but when we are talking about MRAM later we are going to learn about storing information tomorrow. So, at that time you will realize that the perpendicular MRAM is more useful than in plane MRAM. Okay. So, it is very similar to the longitudinal magnetic recording and perpendicular magnetic recording. So, there are many benefits when you store information magnetization in the perpendicular direction. Okay, any other question? Okay, if not, we stop here. So, tomorrow we will learn about how do we store information. So, stay here until Professor Datta comes. So, we will take group picture.
In this orbital torque, orbital Hawking, why did we use chromium? It's already in 3D and we less contribution.
I mean, you can use